All right, so now let's have a little review of counting. So we talked about many different topics in counting, but let's just see a couple of problems and work through them. So problem number 1, how many solutions to the equation x1 plus x2 plus x3 plus x4 equals 17 for x1 through x4 non-negative integers? So this is some kind of counting problem. We should start by trying to figure out what sort of counting problem it is. And it's not immediately clear from the outset, but let's think about how we can try and fit this into some of our frameworks, for example, about putting balls in boxes. So we saw that there's, many counting problems can be thought of as how many ways can you put some balls in some boxes with whatever restrictions or requirements there might be. So can we fit that into, can we fit this problem into the framework of putting balls into boxes? And we've seen that often you need to be a little bit, you need to open your mind a little bit to what the balls in the boxes might be, because they aren't always the most straightforward things. So let's think of this problem like this. How many ways can we find 4 non-negative integers that add up to 17? Well, let's think of 17 as the balls in this problem, and our variables, x1 through x4, are the boxes. So, for example, setting x1 equals 5 should mean 5 balls in box 1. And in this interpretation, you can see that a solution to this equation corresponds exactly to an arrangement of 17 indistinguishable balls into 4 distinguishable boxes. So this is just a number of ways to put 17 indistinguishable balls in 4 distinguishable boxes. And if you remember talking about indistinguishable balls in distinguishable boxes, this is a stars and bars problem. So remember, stars and bars is the way we represent this type of problem, because basically by drawing 3 bars, we create 4 distinguishable boxes, namely this, 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 and this. And then by arranging 17 stars, let me not draw all 17. By drawing 17 stars arranged amongst these bars, we put, for example, this means 2 balls in box 1, 3 balls in box 2, etc. So in this case, we have 3 bars and 17 stars. and the number of arrangements is, this is counting the way we can rearrange 20 objects. So that's 20 factorial, except that 3 of them are indistinguishable, namely the bars. So we need to divide out by the reorderings of those things. And then the other 17 are also indistinguishable. Those are the balls, the stars. So we divide out by the ordering of those as well. So that is our solution for the number of solutions to this equation. It is 20 factorial divided by 3 factorial, 17 factorial. And let's find a number. Why not? This is going to be 20 times 19 times 18. That's this part. So I've left out the 17 factorial. And then divided by 3 factorial is divided by that. So I didn't do this out ahead. Let me compute that very quickly on my calculator. 20 times 19 times 18 divided by 6. And this is 1140. So that is the number of solutions to our equation. Very good. So let's do one more counting problem. I'll get rid of that entirely. How many paths so in 3-dimensional space from 0, 0, 0 to 4, 3, 5 by taking 1 unit steps in positive x, positive y, or positive z directions. So let me attempt to draw a picture to convey what this problem is asking about. We have a cube so let's say maybe this corner back here is 0, 0, 0, and this corner opposite is 4, 3, 5. And we're asking how many paths are there, starting from 0, 0, 0, and taking unit-long steps in various coordinate directions, and always going in the direction of this endpoint, never tracking backwards like that. So no steps backward, only steps forward. How many paths are there? So I don't know if this is the proper number of steps in each direction. I didn't keep track of that. But this is the kind of thing that we're trying to measure. And again, it's not clear from the start what kind of problem this is. We need to fit it into some kind of framework that we have for counting. So what can we recognize in this case that allows us to put this in a more familiar form? Basically, we can recognize that since we know this endpoint and it's always the same, and also since we're only allowed to take unilong steps in the positive directions, the idea is that we know we must take 4 steps in the positive x direction. We must take 3 steps in positive y direction, and 5 steps in positive z direction. And the different paths are just different ways of ordering these. So we can rephrase this into a hopefully more familiar problem. How many ways to arrange 4 x's, 3 y's, and 5 z's? So now this is something that is more familiar. In fact, it's very much like the problem that we changed our stars and bars into. It is counting rearrangements where some of the objects are identical. And we do it in essentially the same way. So what's 4 plus 3 plus 5? Oh, geez. It's 12, I think. Yes, it's 12. So the total number of objects is 12. So 12 factorial is the total number of arrangements, assuming that all our objects are different. And then, to account for the fact that we have 4 identical x's, we divide by 4 factorial to forget the ordering of those. And similarly, for our 3 identical y's, we divide by 3 factorial to forget the ordering of those elements. And for 5 z's, we divide by 5 factorial to forget the ordering of those 5 elements. And let's go ahead and find a number for this. Didn't write this one down ahead of time either, but let's, it can't take more than a minute or two. So it's 12 down to 6. So I'll just leave off the 5 factorial, and that takes care of that guy. And then divided by 4 factorial times 3 factorial. And this shouldn't be, so we can just cancel some stuff like that. That's a 6. 4 and 2 cancels the 8, and that makes the 9 and 3. So let's see, that's not too bad to multiply out. Let's get our calculator. So it's just 12 times 11 times 10 times 3 times 7. So 12, 11, 10, 3, 7. That's everything that's remaining. And this is equal to 27, 720, if I have put it in my calculator correctly. So that is the number of paths through this cube by stepping along the unit axes.